working in a coal mine, going down, 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 working in a coal mine.
Okay, let's get into the homework problems for Chapter 13, the optimization models. And we're going to do two together, and then I'm only going to challenge you to do one on your own here because I know these are a bit tricky. And again, I just want you to get the feel for this. I want you to have this tool in your back pocket. We don't have to be experts at it just yet. But let's start off by, on problem 13.25 here. Before we even go into Excel, we want to pencil out how we might set this up. So it says this: a chemical company manufactures 3 chemicals, A, B, and C. Its chemicals are produced via 2 processes, 1 and 2. Running process 1 for an hour costs 400, yields 300 units of A, 100 of B, 100 of C. Running process 2 for an hour costs $100 and yields 100 units of A and 100 units of B. Note that process 2 doesn't give us any C. To meet customer demands, at least 1,000 units of A, 500 of B, and 300 units of C must be produced. And then what is it asking us to do? Use Solver to determine a daily production plan that minimizes the cost of meeting the company's daily demand. So this time, we're not maximizing profits, we're minimizing cost given some kind of minimum output constraints. I want to think about making sure we include everything in the spreadsheet model. So I'll start out kind of just by spelling out the process, the production process. And I've got process 1 and process 2. We can label their hourly cost, 400 and 100, and then the yield or output of A, B, and C. And process 1 gives us 300A, 100B, and 100C. Process 2 gives us 100A, 100B, and no C. So we might actually set something up almost exactly like this inside the spreadsheet. And we'll highlight these as inputs, right? Hey, what's next? Maybe we should think about the constraints next. So the constraints are this. We have product A, B, and C, and we'll make a little table like we did before, actual, and then the sign of the constraint. In this case, it's going to be greater than or equal to output. And these are going to be basically Excel formulas that tell us how much are we producing according to the hours that we run each machine and the output. So we'll set these up as cell reference formulas. The output over here, we'll know that has to be 1,000 units of A, and this will designate this units per day, 500 of B, and 300 of C. And then we can also set up a check algorithm in Excel to tell us okay or not, whether we're meeting the minimums for what we actually produce. Okay, so these right here are going to be, they're not decision variables for the spreadsheet model, but they're driven by production relationships. So I'll just highlight these in purple to indicate that that'll be a formula that we build into Excel, a cell reference formula. Okay, now the decision. And by the way, you don't have to set things up exactly in this fashion. You could put the decision at the top and the constraints at the bottom. This just happens to be the way that I thought it through. As long as you have everything represented in the spreadsheet and all the cells relating to each other properly, you'll get the right result from the model. But I'm just going to put process 1, process 2, and I'm going to put a solution box here for hours per day that we're going to run each process. And now this, of course, is our decision variable, and this is what Excel is going to optimize for us. So that's going to be the red shaded cells per our textbook convention. And then finally the objective, which remember is cost. So I'm going to put process 1, and then I'm going to put a calculated box for that cost. Process 1, process 2, another calculated box, and then the total here, and that's the thing we're feeding into the optimization model. And remember, we want to minimize that. I'm telling the model to minimize this subject to this right here, given the relationship for the process. Now, how does that work? The actual production for A is the hours of process 1, so we're going to put a cell reference in there, times the yield from process 1. So we're going to put a cell reference there. Likewise for B, the actual, oh, I'm sorry, not done. So that's for process 1. For process 2, we'll put the actual hours of process 2 we run here, times the yield of A from process 2. So that'll go here. So we'll just start plugging in cell references here. So we know the actual amount we get is based on how many hours we run times the yield, how many hours we run times the yield. Same thing for B, right? It's hours run times yield here. Plug in cell references plus hours run here times yield here. Plug in cell references. And then for C, it's hours run on process 1 times yield output, and then nothing for process 2 because process 2 doesn't create product C. So, and that's kind of cluttered, but this is just kind of a map of how we're going to set things up inside of Excel. We get all that stuff set up. We'll have numbers populated here and here. Oh, one final thing, the cost, of course, that's just going to be the hours for process 1. So that's a cell reference here times the cost of process 1. So we drag that cell reference down here. And then likewise for process 2, plug in that decision variable here times this known cost variable here. Okay, so these are all cell reference. Let me, again, in purple, highlight things that we're going to set up as cell reference formulas. Okay, red is things that, we can just start guessing the values of these, and we'll do that. We'll just start kind of plugging in numbers here. We'll see if our check process works. We'll see what our cost is. But remember, our guess and check process is extremely limited. Excel's optimization process is guaranteed to find us that minimum corner solution. And then the gray box down here is what the optimizer is going to solve for us. Okay, so that's a little bit of a mess, but that gives us a map of how to set it up inside of Excel. So let's jump to Excel and set it up accordingly. And keep this in mind, and if you can maybe kind of pencil this out, you can maybe back the video up and freeze frame and pencil that out on a piece of paper to help you set it up, or you can just follow along with me. I've got a piece of paper that I actually penciled it out on first, and I just copied my paper into the drawing program here. And now I'm ready to copy it from the paper to Excel. So let's do production process, hours per day for each machine, 1 and 2, or each process, and then my output of A, B, and C. And then I'm going to populate those variables. This shouldn't be hours per day, it should be cost per hour. So all of my givens about my machines, cost, and their output. Highlight it blue, box it off. This one cost 400 and produced 300, 100, and 100. This one costs 100 and produces 100, 100, and 0. We'll just leave it blank. And the way I'm going to set this up is designate the product A, B, and C. And I'll put the actual production here. We'll put the sign of the constraint there and the requirement here. And then over here we'll run a check algorithm just to make sure we're meeting those constraints. Okay, now the actual will be subject to a calculative process, so we'll leave that blank for now. The constraint, of course, is going to be greater than or equal to, and we know we're going to fill that all the way down. We know the requirements, that's given in the problem. We needed 1,000 of A per day, we needed 500 units of B per day, and 300 units of C. Whoops, 300, not 3,000. And I left this space blank for the designated units, time frame, units per day. Fill that down. And then the check is just basically an if function that says if the requirement is met, if A8, the actual, we wind up producing, is greater than or equal to D8, the requirement, we'll have Excel display OK, and if not, we'll have it display error. Of course, it's all going to be an error now because we don't have any values here, but that's okay. We'll come back and set that up. Okay, next thing I'm going to do is the decision, process 1, process 2, hours per day. You reference back to my sketch. Let's abbreviate this now. Process 1, process 2, hours per day. Oops. And the decision variables, remember we're boxing those in red. Now, guess some values to that, but we need to relate variables to each other before we really do anything else. So we need one more thing, which is the objective that we're optimizing. Cost, of course, we're going to be minimizing it. And we have to have that for process 1, process 2, and then a total. Do a little formatting on this. And these are our objective. Our convention is to color them gray. Okay, and now what we have to do is relate the values in the purple cells, which are the cell reference formulas. So let's start at the cost ones. Those are pretty easy. That's just going to be the amount of process 1 we use, hours per day, times its hourly cost, which is up there. So that's B13 times B3. Process 2, same thing. It's going to be the amount we use times its hourly cost, B14 times B4. And the total is going to be shortcut alt equals sum of what's right above it. Okay, of course, there's nothing there yet because we haven't set the values. Now, finally, the actual production. That's going to be the function of the amount of machine 1, process 1 we use, times process 1's output of A, plus the amount of machine 2, process 2 we use, times process 2's output of A. So there's our total output of A. B, likewise, the amount of process 1 we use times process 1's output of B, plus the amount of process 2 we use times machine 2's output of B. And then finally C equals the amount of machine 1 we use times its output of C. And that's all because machine 2 doesn't produce any C. So that one's easy. Okay, now we're all set. And we can either just optimize right off the bat, or I like to just play around with guess and check a little bit to give us some appreciation for what the optimizer is doing. Let's put 5. Let's say we run each machine 5 hours a day. Are we meeting our requirements? Yeah, my check is checking out. Everything's okay, which means these are greater than or equal to these. So what I start doing now, and my cost is $2,500. Because I want to minimize cost, I start to dial down the amount of each machine we use per day. Let's try 4 and 4. Everything's okay here. Costs have gone down to $2,000. Okay. 3 and 3. Everything's still okay here. My cost is down to $1,500. 2 and 2. Everything's an error here, and my cost is $1,000, but that doesn't matter because I'm not meeting my requirements. So it's going to be greater than 2, less than 3, but we have to start going decimals. We could run for half an hour. We could run for 1 minute intervals maybe. It's going to be a lot of guess and check for us. Is it 2.5? 2.5 work? It works except for everything but C. So guess and check is going to take a while. You actually probably could do it in 5 or 10 minutes because this is a very simple problem. But once we get to just a little bit more complex problem, that guess and check method becomes exponentially more difficult. So bring in the solver. Data, solver, and it's pretty straightforward here. Our objective cell is the total cost. We're minimizing, don't put max. Actually, I'll show you what happens if you run max. It's kind of interesting. Changing the variable cells here, the hours per day for both processes, and then the constraints. And let's do the constraints one at a time so we can have a nice sensitivity analysis. The constraint is the actual amount we need of product A greater than or equal to the required product B. Again, make sure you set that greater than or equal to the required. And finally, product C, and again, set this greater than or equal to the required. And that we should be done. B 8, 9, 10. Okay, we make them non-negative. We're going to use simplex LP. Now, we're supposed to be minimizing. Let me just show you what happens quickly when we maximize. I can't find a maximize the cost. Well, run the things full tilt. We didn't put a constraint about hours per day that we can use the machines. If we had, we would run them 20 hours a day or 22 hours a day, whatever we could maximize, and then run that cost up. Of course, that's not what we're trying to do. So if you get an error like that, you know that there's some fundamental flaw in your logic. Actually, the first time I ran this myself in practice, I got this error and I said, oh, what did I do wrong? Oh, I know. I maximized instead of minimizing. Ran the solver again, and it'll keep everything that you just set up, and this time we'll just plug in the minimum instead of maximum, and we'll solve. And it found us a solution, 3 and 2. And we'll accept that, and we'll know the minimum possible cost is $1,400. And notice we get a little bit more of one of the outputs than we need, but that's required because only A can do product C. And if we run it 3 hours, that's a minimum we can use to get that requirement. Now, the problem asks you to confirm graphically that the daily production plan from part A minimizes the cost of meeting the company's daily demands. I do challenge you to see if you can work the graph, and I'll kind of give you a hint on how to do it, but I'm going to make that a bonus component of the question. I'm not going to require you to do that. I'll give you a couple bonus points if you do. The way you would set that up would be to put the two decision variables on the two axes, so you get process 1 and process 2. It's actually probably useful to just label these as x and y rather than 1 and 2, because I want these to stay variables. I basically just have to say the constraints are the minimum requirement of product A, B, and C. I need 1,000 A. And I want to just plot the intercepts. So if I only use process 1 to get product A, it would take 3.3 hours. If I use process 2, it would take 10 hours. So I'll plot that like this: 3.3 hours of process 1 versus 10 hours of process 2. And I do the same thing for product B and C. Product B, with my requirement of 500 units, I'd be using 5 hours of either process. It creates 100 per hour. So that would look like this: 5 and 5. And product C, I can only make that with process 1, and I need the 300 units a day. It makes 100 units an hour, so that's going to be 3 hours. Okay. And then what I want to do is figure my ISO cost line, which is just this: $400 an hour for process 1, which I'm going to call X now, plus $100 an hour for process 2, which I'm going to call Y now, is a constant. And if I convert that from the AX plus BY equals C format to the Y equals MX plus B format, I can plot it. And if I do that, I'll let you do the algebra yourself. I'm going to get Y equals minus 4X plus C over 100. Slope is minus 4. So I just start plotting a line with slope of minus 4. This slope right here is minus 1, right? So this is going to be steeper, minus 4. It's going to look something like that. And then I say, how low can I go? By changing my constants and still meeting my constraints until I get to right there. Actually, that blue constraint should be a non-binding one. It should be sitting in here a little bit. So I'm going to reach my constraints right there, and then what I would have to do is, and I know that that's where the value of process 1 is at 3 hours. I could solve that on this blue constraint equation, which has a slope of 10 over or minus 10 over 3. Solve for my optimal value of y. Algebraically, it'll come out to 2. And then I plug those values into here and find my optimal cost, which would be 1,400. So you can do, this is like the very first thing we did in this unit. Do it graphically. It's really tedious and involves some algebra. But we're just doing that to validate and kind of have it sink in our minds the structure of what Excel is doing for us. And then never again would we have to do the graph. We'll just let Excel chug away and solve this model for us. The next thing, the only other thing the problem asks us to do is use solver table to see what happens to the decision variables and the total cost when the hourly processing cost for process 2 increases in increments of 50 cents. How large must this cost increase before the decision variables change? And what happens when it continues to increase beyond this point? So let's run solver table. Everything's set up so we can click through. We're doing a one-way. And what were we doing again? We're increasing the cost for process 2 by 50-cent increments. We're increasing the cost of process 2. Okay, so I select the cell reference for process 2. And I'll just call this process 2 hourly cost. And we'll start it at 100, and it said in $50. I think I said 50-cent increments. It's $50 increments, of course. So well, let's go from 100 to 1,000, just to be crazy, and we'll go in $50 increments. And then the effect on the output cells, which of course is the output cells, is going to be the units of each process and the total cost, and control selecting that. And this is one that's going to take a few minutes, probably. No, it didn't take that long. Okay. And I didn't name ranges, which the textbook recommends, but I can just relabel these. B13 and 14 were the units of, or I'll call it hours, process 1, and hours, process 2, and then B19 is total cost. And we can see here how total cost varies and how our optimal decision varies as we increase the cost of process 2. And notice here that up until a cost of process 2 equaling 400, which is the same as process 1, we don't change our optimal mix. And above 400, at or above 400, we do. We shift over to strictly process 1. And process 2 is kind of priced itself out of the market, so to speak. The chart here just lets us select hours P1, P2, or total cost and see how that changes as price changes. So here we have sensitivity of hours P1 to P2 hourly cost. P1 hours they jump from 3 to 5 once P2 cost gets above 400. So that's kind of a nice feature of the solver table as well. So we can then answer those questions here. How large must this cost increase before the decision variables change? It looks like once it got beyond 350. Yeah, once it got above 350, so that's a $250 increase. And then what happens when it continues to increase beyond this point? We realize that we just switch strictly to process 1. Okay, so pretty simple sensitivity analysis for that one. Okay, so we're on to problem 26, and this is the last one that we'll do together, and I'll leave you to do 27 all by yourself. But I think we're maybe starting to get the hang of this now. And this one's actually pretty easy. I penciled it out on paper, so let me show you how I'm going to set this up. As usual, I'm going to just kind of think about the process first. And here the process is really simple. We're talking chairs and desks, and we're talking units of wood that go into each one, and that's 3 and 4. And there's no other process information variables we need to think about, so that's all there is for the process. Those will be inputs, so we'll highlight them in Excel in blue. Okay, now let's move on to the constraints. Excuse my sloppy handwriting. It's partly because my handwriting's sloppy. It's partly because it's difficult to write with these drawing tablets, but we'll get by. So the constraints are threefold. First off, we've got a wood constraint. There's 2,000 units of wood available, so let's put that one in. And as before, we'll put the actual use in first, and then we'll put the sign of the constraint, something like the maximum or whatever, available, something like that. Sometimes it's a maximum, sometimes it's a minimum. And we've got, so this will be a variable based on cell reference, and the sign is going to be less than or equal to 2,000 units of wood. And then chairs and desks are subject to one requirement. Marketing restrictions require that the number of chairs produced be at least twice the number of desks produced. So chairs actual is going to have to be greater than or equal to, and this here, we'll just have it be a cell reference for the actual number of desks. And it's going to be 2 times that cell reference. Of course, there's no constraint on desks, so we don't need to put something over here, but we do need to list it here and have a value so that can feed into the formula for the constraint on chairs. Okay, finally the decision and objective variables. The decision variable is going to look like this. I'm going to lay this one out like I did my very first problem. Chairs and desks. I'm going to put the unit profit margin. And that we know, that's given $400 for desks and $250 for chairs. So we'll just fill that. And then we'll put the sales down below. Now the sales, production / sales, is going to be our decision variables. We'll highlight them in red. This is what we'll be solving for in order to maximize profits. And profits will just be a cell reference. It'll be this times this. And likewise for desks, price per desk times the amount we produce or sell. And then we'll do a total profits, which is just the sum, of course, of this and this. And that'll be our objective. We want to maximize that subject to these constraints here. Okay, so this one I think will actually be really easy to set up. So let's jump over to Excel and do it. Okay, problem 1326. So I'm going to start off, I've got my process variables, and it's just this wood required for chairs and desks. I'm just going to abbreviate all the way through, and that's 3 and 4. These are input variables. constraints. And I'm going to set this up like this: actual amount used, sign of constraint. Let's call this requirement. And then we'll do our check algorithm with the if function. So we've got a constraint on wood and chairs. Chair constraint is tied into the quantity of desks, so we'll put a space for both of them. Sign on wood, of course, it's less than or equal to the available amount, which is 2,000. And our check there is going to be if actual wood used is less than or equal to the constraint amount. We'll tell Excel to say OK, and if it's not, we'll use our conventions here. Error. Chairs are going to have to be greater than or equal to twice the number of desks. So the desk amount times 2. And then my check will be if that is greater to or equal to that number. Whoops, then we are OK. If not, we are error. Okay, so we've got our constraints. Now our decision and objective. Chairs and desk, I'm going to put this across now. Let's call this unit margin. So I'm going to sell the column width. Unit margin was 250 on chairs and 400 on desks. Actual, let's put quantity slash sales. These are decision variables. We're going to let these vary. So those are the red. Highlight per our textbook convention. And finally, profit is simply equal to unit margin times sales. For each, I can actually fill that. Let me make sure my function's right there. Yep, unit margin times sales, and then total equals the sum of those. And I'll label that total. And I'll highlight, actually this time I'll just highlight my, my total profit in gray as my objective variable. Now all we need to do is specify our usage of inputs. So what's the total usage of wood? Well, it is the quantity of chairs produced times the 3 units that each chair uses, plus the quantity of desks produced times the 4 units that each desk uses. What's the quantity of chairs produced? That's that. And the quantity of desks, so this is kind of irrelevant, but we can dial it in like that. Okay, so I think we're all set, and we could just start playing around with, I got a little flub in my formula there. Okay, we can start playing around with volumes. 100, 100. No, that doesn't work because chairs has to be twice desks, so it have to be 200, 100. That's okay, and we make $90,000, but we're not using all the wood, so 400, 200. That's okay on the constraints, and we're making 180,000, but we're actually just using all the wood there. So I think I might have just actually solved it. 500, 250 uses too much wood, right? So we can play around with just dialing in numbers. It's a pretty simple problem. We might be able to solve it, but we're here to learn solver, so let's go to data and run solver. The objective is total profit. We are going to maximize that by changing this quantity output for chairs and desks. The constraints are that the actual wood usage is less than or equal to the available amount right here, and that the actual chair production is greater than or equal to the constraint there. We want to make non-negative. We want to run simplex linear programming, and I think we're ready to solve. And it looks like indeed our maxima, our profits are optimized at 400, 200. So you can see sometimes if the problem is really simple, you could guess your way to the answer, but there's other instances where the problem is going to be a lot more complex and you're not going to be able to guess your way to the answer. And what's more, you know, this problem is going to ask us to do some sensitivity analysis, and guessing and checking for that is really tedious as well. This problem again asks you to confirm graphically. I'll let you try that if you want. Again, I'll just make a couple bonus points, but I'm not going to require you to do that. I want you to know how to run solver and solver table and whatnot, not necessarily how to do the graphical solution. So let's jump down to C, which says use solver table to see what happens if the decision variables in total profit when the availability of wood varies from 1,000 to 3,000 in 100 unit increments. Based on your findings, how much would the company be willing to pay for an extra unit of wood over its current 2,000 units? That's going to be that shadow price of wood. How much profit would the company lose if it lost any of its current 2,000 units? Okay, so availability of wood varies from 1,000 to 3,000 in 100 unit increments. Solver table. That's going to be a one-way table, and we're going to change one of the variables, the availability of wood. So that's going to be input cell right there, B8. And we're going to base it on a minimum of 1,000, a max of 3,000, changing by 100 at a time. And the output we're interested in is all of the decision and objective variables, so the outputs of chairs and tables and the profits. Input cell should not contain a formula. Let's redo that. Let's put it on the requirement. And here's our output of our sensitivity analysis. Now, we want to probably label what's going on here. The input cell along the side, that of course is wood. So that's going down. And then we had chair output, desks output, and profit. And one thing the book does is just calculate the change in profits. So we'll call this delta profit by subtracting the previous level's profits from this level. And that's pretty useful to do. We fill that all the way down, and we see that profit increases steadily by 9,000 as we get extra 100 units of wood. So the problem's asking us, how much would the company be willing to pay for an extra unit of wood over its current 2,000 units? And the answer is quite simple. It adds 9,000 to profit to get another 100 units of wood. So let's call this shadow price per unit. This is delta profit per 100 wood. Let's just go ahead and divide that by 100. That tells us we're willing to pay an extra $90 per unit of wood because it adds up to that much to profit. How much profit would the company lose if it lost any of its current 2,000 units? Actually, we want to start at the output level 2,000 and work our way up and down. So if we worked our way up from 2,000, we'd gain $90 per unit of wood, 900 per 100, 9,000 per 100. And if we went down from there, we would see we would lose 9,000 per 100. Okay, so it's a linear relationship, and if we graph this, we'll see that for profit. Straight line increase in profit as we gain inputs, which is the wood. Okay, so that does it for 1326, 1325, 1327. It's about a farmer optimizing maximizing his profit based on planting wheat or corn and how much fertilizer and labor and everything else he uses. So a pretty realistic scenario for a farmer. And smart farmers, of course, are probably using Excel or similar program to actually make these decisions because they've got pretty objective data from years of experience on what their land will yield, and they have pretty good forecasts of what the crop prices will be. So I encourage you to go into this one, grasping that this is a tool that businesses can actually use, and it's almost infinitely expandable to include all the relevant variables and inputs and constraints. So it's kind of your creativity and your ability to logically reason through the business process is going to be the only limit on your use of this and to enhance your profitability and your efficiency in whatever business you're going to be working in or maybe are currently working in. So I hope you get a lot of usefulness and a lot of value out of this tool in particular, but everything we've learned in Excel.